A natural gas pipeline 120 miles long from Dover to Leeds is constructed at nominal pipe size of 14 inches and 0.250 inches wall thickness with a maximum operating pressure of 1400 psig. The gas specific gravity and viscosities are 0.6 and 8 times 10 raised to power minus 6 pounds per feet seconds respectively. The pipe roughness can be assumed to be 600 micro-inch and the base pressure and base temperatures are 14.7 psia and 60 degrees Fahrenheit respectively. The gas flow rate is 120 million standard cubic feet per day at 70 degrees Fahrenheit, and the delivery pressure required at Leeds is 700 psi. Determine the number and locations of compressor stations required, neglecting elevation difference along the pipeline, assuming compressibility factor Z is equal to 0.9. Now let's begin. Now we first need to find the Reynolds number. So the formula to find the Reynolds number is 0.0004078 times base pressure divided by base temperature times gas gravity times the flow divided by the viscosity divided by the internal diameter. Now let's first find the internal diameter. Now the nominal pipe size is 14 inches while the wall thickness is 0.25 inches. So the internal diameter will now be 14 inches minus 2 times the wall thickness, which is 0.25. So this will give us what? 13.5 inches. So D is 13.5 inches. Now they give us gas gravity. Now let's write down the given data. They give us gas gravity to be 0.6. They give us a flow rate to be 120 times 10 raised to power 6 standard cubic feet per day. Now we are also given the base pressure to be 14.7 psi. The base temperature is given as 60 degrees Fahrenheit. So we now have to convert it to Rankine by adding 460. So it gives us 520 degree Rankine. Now we are also given the viscosity to be 8 times 10 raised to minus 6 pounds per feet seconds. Now we are given the maximum operating pressure of the pipe to be 1400 psi G. The delivery pressure, let me call it P2 to be is 700 psig, and then the length of the pipe is 120 miles. The roughness of the pipe is 600 micro inch, which is your E. And the temperature of the gas is 70 degrees Fahrenheit, which is 70 plus 460. This will give us 530 degree Rankine. So if that is all given now, let's now find the Reynolds number, which is 0.0004778 times 14.7 divided by 520 times 0.6 times 120 times 10 raised to the 6 divided by 8 times 10 raised to the minus 6 divided by 13.5. Now let's make use of our calculator. Now you can make use of a calculator to punch this, while I make use of my calculator on my own end. So now 0.00478 times 14.7 divided by 520 times 0.6 times 120 times 10 raised to the 6 divided by 8 times 10 raised to the minus 6 divided by 13.5 divided by 13.5. So our Reynolds number is 9,004,692. This is our Reynolds number. So since the Reynolds number is more than 4,000, so it's a turbulent flow. This is a turbulent flow. We are going to make use of this formula to find the friction factor. So which is 1 all over the square root of the friction factor is equal to minus 2 log to base 10 bracket open E divided by 3.7 internal diameter plus 2.51 divided by the Reynolds number square root of F. Now let's assume F is equal to 0.01. Now let's solve for X in the left hand side. Now we substitute F equal to 0.01 in the right hand side. Now what we get, we will now solve for the F in the left hand side. If what we get is equal to this, then we have come to the end of the iteration, because we'll be doing an iteration. This will be an iteration method. So now 1 all over the square root of f is what now equal to minus 2 log is 10. The e is 600 times 10 raised to the power minus 6 divided by 3.7 divided by 13.5 plus 2.51 divided by 9,004,000, which is 4,692 divided by 0.01. Now we're looking for this. We have substituted this assumed value here. So let's calculate the whole of this. Now let's see what it gives us. And then we can now find our f. So now make use of our calculator, say minus 2 log 2 base 10 bracket open 600 times 10 raised to power minus 6 divided by 3.7 divided by 13.5 plus 2.51 divided by 4,692 and divide by square root of 0.01 equal to, so this will give us 9.6595089824. Now the square root of f will now be equal to the inverse of this answer. So now we inverse the answer. So now what we're going to do is the inverse of the answer. This will give us what? 0.103.524,93091. Now we will take the square of both sides. We will now have our f. So square both sides. So now if I square this, I have 0.01072. So this is our f value for this. Now let's assume this f value, since it's not the same with this, let's assume this f is equal to 0.01072. Now solve. And let's solve for f again. Now we are going to have 1 over the square root of f equal to minus 2 log this 10 e, which is 600 times 10 raised to plus 6 divided by 3.7 divided by 13.5 plus 2.51 divided by 9,004,692 square divided by the square root of 0.01072. Now what will be the result of this? Now let's go there. So we will now have minus 2 log base 10 bracket open 600 plus 10 raised to power minus 6 divided by 3.7 divided by 13.5 plus 2.51 divided by 4,692 divided by square root of 0.01072 equal to this. We have 9.665 116,43456. So now the F will now be the inverse of this. The inverse of this and square it. So let me square of this. So F will have 0.01070. So it now implies that F is equal to 0.0107. Now let's calculate. Now let's assume we are using one compression. Now here is 700 psi G. Let's assume now we're using one compressor where you compress from here. Let's look at what. Okay, here is 120 miles. Now let's look at what will be the pressure here if we're using one compressor where the discharge pressure. What should be the discharge pressure of this compressor here that would deliver 700 at this at lead from Dover? Now let's say the discharge pressure. Let's look for the discharge pressure here. Now let's make use of flow equation. So we now apply the flow equation where you have Q will now be equal to 77.54 times base temperature divided by base pressure times P1 square minus P2 square divided by G, the gas gravity, divided by the flow, the gas flow temperature divided by the length of the pipe divided by compressibility factor divided by friction, all raised to power 0.5 times the internal diameter raised to power 2.5. Now we have let's go to the next page. Now let's just write this flow rate. The unit is standard cubic feet per day. The base temperature is in Rankine. The base pressure is in PSIA, sorry. The P1 is the upstream pressure in PSIA. The P2 is the downstream pressure in PSIA. We have the gas gravity dimensionless, the gas temperature at Rankine. The L is in mile, the Z is dimensionless, the F is dimensionless. Now, so we have somehow roughly defined this. This is a volume flow rate in standard cubic feet per day. This is the base temperature in Rankine. This is the base pressure in PSIA. This is the upstream pressure in PSIA. This is the downstream pressure in PSIA. Now we also have internal diameter in inches over here. Now let's apply what we just have written down. Now the volume flow rate is 120 times 10 raised to power 6, which is equal to 77.54 times. The base temperature is 520 in Rankine, and the base pressure is 14.7. Now times P1 square minus, now we have our downstream pressure, which is the delivery pressure, at 700 psig. Now to convert it to psia, we add 14.7, so we have 714.7 square divided by G, which is 0.6, divided by the gas temperature, which is 530, divided by the length of the pipe, which is 120 miles, divided by the gas gravity, which is 0.9, no, the compressibility factor, which is 0.9, and the friction factor, which is 0.0107, all raised to power 5 times 13.5 raised to power 2.5. Now let's solve for P1. Now to solve for P1, we can just say P1 square minus 714.7 square divided by 0.6 divided by 530 divided by 120 divided by 0.9 divided by 0.0107, all raised to power 0.5 will now be equal to, now will now equal to 120 times 10 raised to power 6. Now times this 14.7. Now divide by this. This is 7.54. Divide by 520. Divide by 13.5 raised to power 2.5. Now that is it. So now if we square both sides, this 0.5 will go. Now if we just say squaring both sides, now we have this will cancel out this. So now we have P1 square minus 714.7 squared divided by 0.6 times 530 times 120 times 0.9 times 0.0107. Now let's work this out. Let's see what it gives us. Now so say 120 times 10 raised to the power 6 times 14.7 divided by 77.54 divided by 5 pay in 520 divided by 13.5 raised to power 2.5. So this will give us then square. To square it, so what will it give us? The square it gives us 4,268.448 427 241 23. So now so P1 square will now be equal to 714.7 square plus, now we use the whole of this that is in the denominator to multiply this. So we now have 0.6 times 530 times 120 times 0.9 times 0.0107 times 4 times the whole of this 4268.448 427 24122. Now P1 will now be equal to what? Let's see. Now we're multiplying this value here with 0.6 times 530 times 120 times 0.9 times 0.0107 equal to this plus 714.7 squared equal to this. Now take the square root of the answer. So we now have P1 to be 1442. PSI now we can convert it to psig by minusing, so say 1442 minus 14.7. So we change it to psig to be 1427.3 psig. So now, so since the pressure P1 is equal to 1427.3 psig and is greater than 1400 psig, which is the maximum operating pressure. So it means that one compressor cannot function properly because it will be giving us a pressure greater than the maximum operating pressure of the pipe. So since it's giving us this higher than that, so what I am proposing is a two compressor system where now at now here is 700. This is another. So now I am proposing a system like this. So a system like this. Now from here like this. So now here should be like 700. Now what I'm proposing, I want a situation where this is located at the middle. So here is 60 miles. Here is 60 miles. So now the other compressor is located at the middle. While this one is here, takes in gas at 700 psig and delivers it at a particular pressure, at a delivery pressure. It comes here at 700, delivers at a particular pressure. So now let's calculate the pressure. So now what I'm going to do is this. Let's calculate this pressure here. What will be the delivery pressure? That's what we're looking at now. So I'm using 60 miles. Now we're going to make use of this flow rate formula again. The flow rate remains the same, which is 120 times 10 raised to power 6 equal to 77.54 times 520 divided by 14.7 times. Now we're looking for P1 square minus 714.7 square divided by 0.6 divided by 530 divided by, now here becomes 60, not 120, divided by 0.9 divided by 0.0107, all raised to 0.5 times 13.5 square, 7.5 raised to power 5 and 2.5. Now let's work it out now. So we have P1 square minus 714.7 square divided by 0.6 Then 530 divided by 60 divided by 0.9 divided by 0.0107. Now should now be equal to 120 times 10 raised to the 6 times 14.7 divided by 77.54 divided by 520 divided by 13.5 raised to power 2.5 all squared. Now, so 120 times 10 raised to power 6 times 14.7 divided by 77.54 divided by 520 divided by 13.5 raised to power 2.5 equal to the square. Now we'll now say p1 square will now be equal to 714.7 square plus 4268.448 427 24122 times the whole of this in the denominator, which is 0.6 times 530 times 60 times 0.9 times 0.0107. So I just say times 0.6 times 530 times 60 times 0.9 times 0.0107 plus 714.7 square equals to this. So now we'll now look for P1, that's the square root of this answer. U1 138 PXIA, which is 1138 minus 14.7 will now give us 1123.3 psig. Now that means the compression ratio of the two compressors, identical compressors, that's what we're going to use. So with two compressors, so P1 divided by P2, the compression ratio will now be 1138 divided by P2, which is 714.7. So this will give us what? So 1138 divided by 714.7 will give us compression ratio of 1.59, is roughly 1.6, compression ratio of 1.6. So it's a two compression system, 1.59. So this is what we can use. Now that means here the one, let me see, 1123.3, 1123.3 psig. Now here is 700, so here is 1123.3 psig. So this is it. So this is it. Now, so it will now give us a delivery pressure of 700 here. Two compressor. So the answer should be two identical compressors of compression ratio of 1.6 and a delivery pressure of 700. Now it will have a discharge pressure of 1123. Now meaning that it will have, now here we need a delivery pressure of 700. So now the compressor will now have a suction pressure of 700 psig and a discharge pressure of 1123.3 psig. So, and it will be an identical compressor, a compression ratio of 1.59 or roughly 1.6. So now we have come to the end of this class, this problem. Now, thank you for watching to the end. Have a nice day. Also, do well to subscribe to my channel. So when next time I make new video, you will also be the first to watch. Thank you and God bless.